let's talk about spinors, specifically non-relativistic spinors. So often in physics and mathematics, we define things in a most concrete and intuitive way that we can. However, sometimes if we allow a more abstract definition, that allows us to extend the applicability of the idea that is at hand. For example, if we define our trigonometric functions, we start with by defining our trigonometric functions in terms of physical triangles that we can construct, or real triangles that we can physically construct, right? Okay, so before I proceed any further, I would like to point out some of my, you can say, silly kind of notation that I'll use for sine, cosine, and tangent. So if I am talking about sine of theta, I write it like this. That is sigma, and under sigma I write theta. So that is sine of theta, right? Let me actually just write it down first. So this is my sine of theta, and this funny looking gamma, and under that if I write theta, that is simply cosine of theta, and tau and theta inside that tau is simply tan theta, right? So this is my silly notation that I'm going to use for sine, cosine, and tangent. It's just my way of writing it, so you know, it is I find it useful because it is a very shorthand notation, right? Okay, so getting back to the topic now, I was talking about that we first defined these functions, trigonometric functions, in terms of real triangles that we can physically construct. So we, in terms of real triangles, we draw a triangle, a right angle triangle, and we label one of the angles as theta, right? So then the ratio of the sides, we can use those ratio of the sides, and we can define sine of theta, tan of theta, and cosine of theta. In fact, one way to calculate cosine of theta is to create this right angle triangle, and one of its angles, we'll label it as theta. Then what we do is measure the length of the adjacent side, that is in this case this side, and divide it by the length of the hypotenuse, so that is this one, right? And so then we have our cosine of theta is equal to adjacent divided by hypotenuse, right? So this is just one of the examples of in how we start defining our trigonometric functions, but and this definition and its utility is actually rooted in our immediate perception of the geometry. But let's say, how do we define then cosine I theta, that is this thing, I theta, where of course iota is our imaginary number, that is square root of -1. How do we define this in terms of this triangle, right? Certainly we can't build a triangle with one side of imaginary length, much less measure it. So what we can do is, if we allow ourselves to define cosine theta in terms of its Taylor series or Taylor expand cosine theta, that is something like cosine theta is equal to, if you recall, the Taylor series expansion of cosine theta, which is, of course, it's a much more abstract way of doing it, right? In terms of drawing this triangle that we can physically construct, and we can take a ruler and measure these sides, and we can take a protractor and measure the angle. Of course, these measurements are not exact. So if you measure the angle with a protractor, it is always going to be off by a degree or so, right? Okay, so coming back to this, we can write or define cosine theta in a much more abstract way, that is, in its Taylor series, that is 1 minus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cube. I'm sorry, this should be actually 1 over 4 factorial times x power 4. And well, so on. So we have these even numbers over here, right? So in this way, we can define cosine theta. And then, of course, we can also define cosine iota theta, right? I would also like to point this out that I used x over here. This should be theta because I'm writing cosine theta, right? I'm defining cosine theta, so these x should be actually thetas. Now, I can simply substitute in place of theta, iota theta, right? And so that's how I can define my cosine of iota theta. Yeah, so actually let me write it down. So I have cosine of iota theta can then be defined in terms of this Taylor series as 1 minus 1 over 2 factorial times iota theta squared plus 1 over 4 factorial times iota theta 4 power 4, right? And well, of course, so on. And so this writing cosine in terms of its Taylor series is obviously definitely an abstract way of defining cosine theta, but this abstractness then allows us to even define cosine of iota times theta, right? And so with this, it also allows us to see this connection between cosine hyperbolic. So my cosine hyperbolic of theta is something like this, which is equal to exponential of theta plus exponential of negative theta over 2, which is equal to cosine of iota times theta, right? So this abstractness or this abstract definition of cosine theta allowed us to see this connection between the hyperbolic trigonometric functions and cosine I theta, right? Now, moving on, we are going to talk in terms of groups, specifically Lie groups and Lie algebras, to see or to define spinors, right? Actually, spinors are just going to pop out of our definition of groups, SO3 and SU2, right? Okay, so most of the groups that we use in this are examples of Lie groups. These include the standard model groups, that is SO13, that is SU3, SU2, and well, so on, U1, as well as purely spatial rotations, right? So those are purely spatial rotations are SON, right? Okay, so let's recall or quickly define a Lie group technically. So we're going to talk a bit about Lie group. A Lie group forms a manifold with a differentiable structure, right? And what is important about this is that if we know how to do something infinitesimally, then we can almost figure everything else out as well, right? So again, a differentiable structure, we said that a Lie group forms a manifold that has a differentiable structure. So in this case, we can talk, a Lie group is then a continuous group, right? So let me give an example. If we know a matrix that rotates in a YZ plane, right, by say 1 degree, so what would that be? That would be R YZ 1 degree, right? So what this tells you that there is a matrix that rotates in a YZ plane with 1 degrees. then we can certainly use this and build any integer rotation in yz by simply compounding these rotations, or these operators, you can say. For example, let's say you have ryz 45 degrees, right? So you want to perform a rotation in yz plane of 45 degrees. Well, you can simply do that with this, right? And how you can do that is you take this ryz 1 degree and you apply this operator 45 times. So that is to the power 45. So each time it will perform a degree of 1 rotation, and it will do this for 45 number of times, right? And so therefore eventually you will end up with a rotation of 45 degrees. Now, of course, we don't want to limit ourselves to integer transformations, and so then we need to start with an infinitesimal rotation, something like r in yz of, let's say, this delta theta, where this delta theta is infinitesimal, right? Okay, now the hard part is then of figuring out how to compound infinitesimal transformations to get a finite transformations. Well, that's where these Lie groups come in, because they come equipped with a way to do this, right? And so now we're going to move on the formal way of, or the formal definition of a Lie group, or let's say we're going to talk about Lie groups formally, right? Okay, so in a Lie group, a general element of a Lie group can be written as A is equal to exponential iota G A V A, right? Where this G A is the generator and V A, this thing, is the parametrization, right? Or it is a parameter. Okay, so again, A, this thing, is a general element of a Lie group, right? General element of Lie group. GA is the generator. It generates a transformation, right? So that's what a generator is. It generates a transformation. And VA, it is a parameter which parameterizes the transformation, right? So it's a parameter, and its job is to parameterize the transformation, right? Now, note that if A is n cross n, then this implies so is the vector GA, or the matrix GA, is also n cross n, right? And this GA times VA, this whole thing over here, this allows us to combine different types of transformations. Say, for example, you can write GA VA is equal to GXY theta plus GYZ phi plus GZX. Another variable that I can use for angle could be, let's just say, psi, right? Okay, right. Now let's go for an example, or let's do a case study of SO3, right? SO3. Okay, so in SO3 we can write a rotation in YZ about YZ with some angle theta can be written as the exponential of iota, now g, this g will have yz, because we are doing the rotation in yz plane, times theta, where this g of yz is actually a vector of matrices, right? Okay. Now, well, because it is a vector of matrices, it's actually a matrix. So how do we exponentiate a matrix? Well, to exponentiate a matrix, what you do? You simply expand it in a Taylor series. So you expand this exponential in a Taylor series. So Taylor expand it. Right? So let's go ahead and do that very quickly. Say we have this thing, exponential iota g in subscript ryz times theta can be written as, if we Taylor expand this exponential, we have identity plus iota g ryz times theta minus 1 over 2 factorial. So all I'm doing is I'm expanding the exponential function, right, in Taylor series. So you have g ryz squared times theta squared plus 1 over 3 factorial times iota g ryz times theta cube plus, well, so on, right? Okay, so now note that in principle, what do we want to figure out? What we want to figure out is this thing, right? GRYZ. What is this? That is what we want to know. So if you recall, in 3 cross 3 matrix of rotation, ryz about theta is equal to 1 0 0 0 0, and then we have these trigonometric functions, that is cosine of theta, sine of theta, negative sine of theta, and cosine of theta, right? Now what we can do here is, if we Taylor expand these sine and cosines, so we Taylor expand sine and cosines. When we do that, we can go ahead and simply compare it with this equation that is over here, this equation of exponential, and we can compare these expansions, and what we arrive at is, then we arrive at g ryz can be figured out from that by that comparison, that is simply equal to 0 0 0 0 0 0 minus iota and 0, right? It would be a good task for you to do this by yourself. It is not that messy, but it does kind of get a bit well, hectic, right? But of course it can be done, and you can do it, and you can compare it by yourself by expanding this rotation matrix in Taylor series, expanding the sines and cosines, right? All of these, you can expand them in Taylor series, and you can go ahead and compare it with this exponential equation, this exponential expansion, and you will arrive at this GRYZ, right? So you will arrive at this matrix for GRYZ. Now, let's see its properties very quickly. So if you square this GRYZ, if you square this matrix, what you get is simply 0, 0, 0, 0, 0, 1, 0, 0, 1. So if you notice that this thing forms an identity, right? And another one could be if you go ahead and cube this GRYZ cube, that simply returns you back your GRYZ, right? Okay, now note that the G's themselves are not elements of SO3, right? G's are not the elements of SO3, but when we use this exponential map, this one, right, the R's that they create, there are these R's, they belong to SO3, right? So G does not belong to SO3. However, the R's that we get from this G, they definitely belong to SO3, right? That is, if you take R and times R transpose, that is equal to identity. That is one of the properties of SO3, and the determinant of R is +1. And so we do this, we check this, and we get these results. And so these results simply mean that R belongs to SO3. And so the generators are not the elements of the group, right? Because recall again, we said that G are the generators, and they are not the elements of of the group or SO3, right? Okay, now the next question can be that can we define SO3 rotation matrices without ever needing to define the coordinates, right? So instead of defining the coordinates that were this theta, phi, and psi, can we simply define SO3 matrices without using them? Well, that's where the Lie algebra is going to come in. And so we can specify the Lie algebra of a group of this SO3. It is written as G RYZ, the commutator of this, right? So GRYZ, ZX, for example, is equal to GRYZ. I'm just opening this commutator now, right? Times GRZX minus GRZX times GRYZ, right? So I've just opened the commutator, and now if I compute this, what I get is iota GRXY, right? So if you look at this carefully, we can simply go ahead and generalize this Lie algebra for this group SO3, and we can generalize it as the commutator of GI and GJ is equal to iota times this Levi-Civita ijk times gk, right? And so this is how we define rotations in 3 dimensions with the help of this Lie algebra, right? So we can define the rotation operators in SO3, the rotation operators for SO3 in 3 dimensions with this Lie algebra, right? Okay. Now, for almost any of the groups, we can write the Lie algebra as the commutator of Gi Gj is equal to some f I jk times gk, where this f ijk is known as the structure constants of the group, right? So it's the structure constants of the group, right? And it just happens to be that for rotation, the structure constants are this antisymmetric Levi-Civita, right? Okay, moving forward, let's ask the question that is there a 2D representation of rotations in 3 dimensions, right? And what this question is going to do is, this is a very important question because this question is going to lead us to the definitions of spinors, right? The non-relativistic spinors, right? So again, the question is there a 2-dimensional representation of rotations in 3 dimensions? So if we play a bit around with the algebra, we get the 2-dimensional matrices that are going to work for our question, and these 2-dimensional matrices are grxy is equal to 0, 1 half, 1 half, 0, right? This is one of them. The other one is grYz, which is 0, negative iota over 2, iota over 2, 0. And lastly, we have grzx, which is equal to 1 half, 0, 0, minus 1 half. Right. Now, if you look at these, they are very familiar to you actually, because these matrices are, this one for example is simply this sigma x over 2, where the sigma x is just our Pauli spin matrices, right? And this one over here is our sigma y over 2, and this one over here is sigma z over 2. Right. Now let's quickly recall that general element of a Lie group can be written as, we said earlier, it is A is equal to the exponential of iota g a v a, right? Now if we put in our g's, and in place of va it is a parameter, and so we are parameterizing it with theta, so this is equal to exponential of iota g, let's say g alpha. Now alpha is defining this rxy, ryz, or is it rzx, right? And times the parameter, which is theta. So once we do that, we get a matrix that is, let me write it down, that is cosine of theta over 2 iota sine of theta over 2 sigma, sorry, sine theta over 2 and cosine theta over 2. I hope you don't get confused with these sigmas that I used over here. Those were the Pauli spin matrices. But over here, when I wrote this matrix, this sigma is, as I mentioned in the start of the video, these are your sine, cosine. This sigma over here is sine, right? So sine theta over 2, right? So let me just quickly repeat this thing. This is cosine theta over 2. This is iota times sine theta over 2. This is sine theta over 2. And this is cosine theta over 2. Right. Okay. Now, if we look at this matrix, we have constructed this matrix. And this matrix, let me write it down on the next page. This matrix, that is, I write this down again. So it is cosine theta over 2, iota sine theta over 2, iota sine theta over 2, and cosine theta over 2. Let me just go back and check. I missed an iota over here, right? Okay, so coming back over here, this matrix belongs to SU2, right? So we asked the question earlier that is there a two-dimensional representation of rotations in 3 dimensions? So what we did was then I said that we play around with the algebra and then we get these two-dimensional matrices which are going to work for our case, for the question. And so those were the G's that we wrote. That is GRXY, GRYZ, and GRZX that we wrote over here on at the top, right? And then we used our definition of a Lie group that we said an element of a Lie group can be written as A is equal to exponential of whatever is in the exponential, right? And then we substituted these 2 cross 2 G matrices and we figured out this matrix, right? That is over here. And this matrix is an element of SU2. So we can say then that this matrix over here, it is going to act on complex 2-component objects, right? 2-component objects. So let me write over here. Let me also write that this acts on. So this matrix that is over here, it is going to act on complex 2-component objects, and let's just write them as chi. And these complex 2-component objects are called, or we define them as spinors. So this chi is spinor, right? And so these 2-component objects are our spinors. Then, now what we did over here is we derived the 2-dimensional matrix for SU2, but we used the algebra for SO3, right? So when I said that we play around with the algebra to come to such these 2 cross 2 matrices, we used the algebra of SO3 and we arrived at these G's. And so what we can say then is, at least near the identity in this vector space or manifold, near the identity, SO3 is equal to SU2, right? So what is equal, right? So we can say that their Lie algebra is identical near the identity. okay, I'm saying near the identity, right? What if I ask that is it true globally, right? So not just near the identity, but in all of the space. Well, the answer is then no, and we can prove that simply if we take, say, SO3, take SO3, and you take the element R and do a rotation of 2 pi. So what you get is, this is 1, 0, 0, 0, 1, 0, 0, 0, 1. What is this? This is your identity, right? Now, if we take from SU2, we take the same R and do a rotation of 2 pi, right? We arrive at -1, 0, 0, -1. And that is negative identity. So these two are not equal, even though we did an equal amount of rotations. So if we took an element in SO3, we performed a rotation of 2 pi, we arrived back at that element, right? However, in SU2, if you take a rotation of 2 pi, you do not arrive back at that element. In fact, you arrived at the opposite side, that is negative, right? So for a spinor, because we came to this concept or this idea of spinors from SU2, right? And so for a spinor, you will have to perform a rotation twice to come back to its original position, right? And so physically, if you try to imagine this, it beats your head, right? But in an abstract way, a spinor is something that you have to rotate 2 times to get back to its original position, right? So for SU2, you do R 4 pi. What is that? That is simply R 2 pi, R 2 pi, which is nothing but -1 multiplied by -1, which will give you a positive one, or positive identity, right? So again, for a spinor, you have to rotate it twice to come back to its original position. Rotate with an angle of 2 pi 2 times. Or you have to perform a rotation of 4 pi radians to come back to its original positions. So in a way, we can also say, or some physicists say, that spinors know about the square root of the geometry. And so spinors also satisfy the Clifford algebra. So we talked about Lie algebra. Lie algebra, we used a commutator, right? But in Clifford algebra, we define Clifford algebra with anti-commutator. So we can write the Clifford algebra for the spinors, that is sigma I sigma j anti-commutator is equal to 2 times delta ij, where I and j in this delta are the space indices, times the 2 cross 2 identity, right? And this delta ij, if you recall, this is simply 1 0 0 0 1 0 0 0 1, right? Okay, another illustration of this spinors of what we're talking about can be from quantum mechanics, in where you start with 2 integer spins, for example, and you can combine the two integer spins to form another or other integer spins, right? However, if you start with half integer spins, you can combine them to form not only half integer spins but also integer spins, right? So if you take, for example, a half integer spin and another half integer spin, you combine them to form integer spin, that is spin 1. But you could also take a half integer spin and you could take a 1 integer spin, and you can combine them to form a half integer spin, that is 3 halves, right? Okay, so now to finish up, we need to determine how to build an invariant, that is for the Lagrangians, out of these spinors, right? So let's go to another page and we follow our usual recipe. Say if chi, which I said that these are our spinors, if chi goes to some chi prime, this transformation would be equal to exponential iota over 2 sigma dot theta, right? So sigma dot theta, where then the sigma is our Pauli spin matrices vector and theta, right? Okay, and times, of course, times chi. And so we can also define, we can write chi tilde goes to chi tilde prime, right? My pen is not working. Okay, chi tilde prime is equal to exponential iota over 2 sigma vector dot theta vector times, we take this transpose and inverse of this. So we take inverse and we take transpose and we have chi tilde, right? In this case, the chi tilde times actually chi tilde dagger, where dagger is simply you take the complex conjugate and then the transpose. So chi tilde dagger, chi is invariant, right? And you can see that from the above expression that I wrote, right? But recall how we form chi tilde from chi. We can form that by chi tilde is equal to g chi, where let me write this down, where exponential iota over 2 sigma vector dot theta vector, the dagger of this, and g, so we are sandwiching g between these two expressions. Let me write this: exponential iota over 2 sigma vector dot theta vector. This is equal to g, right? However, for SU2, we already know that u times u dagger is 1, right? So for SU2, you know that u times u dagger is 1. So g is equal to identity, right? And we can say that chi tilde is equal to g chi, which is equal to chi, right? Because we got this G as identity, and so if we take this thing, we get back our chi. And so again, this tells you that chi times, chi dagger times chi is invariant, right? So for spinors, we build an invariant, out of spinors, we build an invariant that is used for the Lagrangians, right? Okay, this was we're pretty much done, right? We are done with the non-relativistic case of spinors. So everything that we discussed was non-relativistic. But in a later video, we are going to talk about how to do relativistic spinors, and we shall develop the relativistic story of the generators. Then we are going to find the Lie algebra, and from that Lie algebra, we will look for the spinor representations, right? So yeah, that's it for this video.